Then it is my pleasure to introduce the first speaker of the session, Hannah Keller, who came here yesterday from Denmark. And while the slides are being fired up, she will be speaking about module learning with errors with truncated matrices, if I remember this correctly. Great. Slides are up. Hannah, the floor is all yours.
Great. Thank you. This is some joint work with Katarina Budgust on module learning with errors with truncated matrices. So in this talk, the focus is the module learning with errors problem, which, as many of you will know, is one of the most commonly used hardness assumptions in lattice-based cryptography. In its standard version, we have a matrix A that is sampled uniformly at random, a seed vector, which is also sampled uniformly at random, and an error vector that's sampled from some error distribution, often the discrete Gaussian. I will consider the quotient ring, RQ, for ring R and positive integer Q, and power of 2 cyclotomic rings in this talk, and I will use coefficient embeddings to identify elements in RQ using polynomial coefficients. In this problem, then, the goal is to solve these noisy linear equations. In the search variant, we want to output the secret vector S, given the LWE sample, AS plus E, and the matrix A. And in the decision variant, we want to distinguish an LWE sample like this from a uniformly random sample. Besides discrete Gaussian error distributions and uniform distributions for seeds, and secrets and matrices, we can also consider other distributions for the error, secret, and matrix distributions. And some previous works study different distributions for the error and secret distributions, but only relatively few study hardness for LWE where the matrix doesn't follow a uniform distribution, and that's the focus of this work. To give some context about what is known for non-uniform matrices, we can start off with a simple example where we have a matrix with only binary coefficients. We have a reduction to this from standard MLWE, and that reduction basically just includes a bit decomposition and then increases the dimension in the matrix by a log Q factor. One related work generalizes this for other distributions to cover ones like discrete Gaussians, as well as linear or uniform distributions over linear subspaces. And there are also some other works that cover matrix distributions that are close to the uniform distribution, computationally, statistically, or in Renyi divergence. But all of those works don't cover the distribution that is the focus of this work, which is truncated matrices, where basically the lowest order bits are deleted from a uniformly sampled matrix. This seems like a natural or useful distribution to save in bandwidth. For example, in public key encryption schemes based on LWE, we have the public key which includes this matrix, and so naturally deleting some of the bits might yield some public key compression. However, the only work so far that gives a reduction for truncated learning with errors does so from the module variant of the NTRU problem and is restricted just to the search variant of the problem. So because the NTRU assumption is seen as less standard than MLWE, and because the search variant is not enough to cover applications like in CPA, security of encryption schemes, we ideally would like to show the hardness of decision truncated MLWE from standard MLWE in the decision variant. Now, a little bit more specifically, the matrix in the setting is first sampled uniformly, and then we choose some parameter or constant, lowercase c, where now the lowest order bits of every coefficient in every entry in U are deleted or truncated. And to give some intuition or observation about what we need to show hardness for this, intuitively you can notice if, for example, we truncate 2 bits, like on the slide here, then Clearly, the product of A and S will still have zeros in the lowest order bits, and we require that the error needs to cover more than those two least significant bits in order for the problem to be hard. And this is covered by all of our applications, and just as a starting point. Now, from that, our contributions are to show the hardness of truncated LWE, both for search and decision variants from standard module LWE. For the search variant, we use an approach based on the Renyi divergence, which has some nice, useful properties. Specifically, this reduction is flexible in terms of the error distributions that can be used. We give some applications of the discrete Gaussian, discretized or rounded Gaussian, and bounded uniform distributions, but other distributions could be used here too. Unfortunately, though, the Renyi divergence-based approach leads to only vacuous results for the decision variant, so we need a different approach for that. For that variant, we show hardness using an intermediate variant of LWE known as hint LWE. And because there is a reduction from MLWE to hint LWE, we can give another reduction from hint LWE to truncated LWE to complete this chain and show hardness. First, I'll give some details on the approach for the search variant using the Renyi divergence. So first, you can recall our definition of truncated LWE, where the low order bits in the coefficients of the matrix are cut. And now we can view this truncated matrix as the difference between the original uniform matrix and the deleted low order bits. Then we can rearrange the terms, and we can think of this as a standard MLWE sample, where now the error comes from a different distribution, or rather a shifted distribution, which is a sample from the original error distribution shifted by the matrix vector product of the low order bits in the matrix and the secret. Now, if this were a fresh LWE sample with an error distribution from which LWE is known to be hard, then we would be happy and finished. But the problem is that the error distribution depends on the secret and might leak some information about it. We can argue, though, that this new error distribution is independent of the secret as long as the distribution is sufficiently large. And to do that, we want to measure the distance between the shifted error and the error sampled from a distribution from which we know LWE is hard. And if we can ensure that that distance is small, then we can argue hardness. So as you might have anticipated, we use the Renyi divergence to quantify the distance between these two distributions. I won't explain how the Renyi divergence is defined. We just need it to be small. And in order to bound its value, we need a bound on this shift NUS. In order to do that, first you can notice that every entry in NU is bounded above by 2 to the C, since it's made up of the C least significant bits. And we have a requirement in our reduction that the secret distribution needs to be bounded so that every entry in this secret vector is bounded. One thing now that I will say about the Renyi divergence is to introduce the probability preservation property, which basically says that there's a multiplicative dependence on the Renyi divergence when we're relating the probability of obtaining some sample from one distribution or the other. We can use this, property to relate the advantage of a truncated MLWE adversary to the advantage of a standard MLWE adversary. And this basically implies that if the original problem is hard and the Renyi divergence is small, then the truncated LWE problem will also be hard. You can also note that requiring this divergence to be small will imply that the samples from the error distributions need to be much larger than the shift that depends on the secret, which implicitly excludes this setting I talked about at the beginning where the error sampled from the distribution doesn't fully cover or hide the secret. And also one last point that I skipped over here is that we can just focus on the sample itself, because removing the low order bits of the matrix A only results in less information being transmitted. As of today, the only way we know to use the Renyi divergence arguments for decision variance is to make use of the so-called public sampleability framework. The truncated MLWE problem does work well with this framework because given some truncated LWE sample, it's possible to get fresh samples by drawing new secrets and errors. But the loss in advantage here depends on the Renyi divergence between the standard way to sample the matrix and the truncated way. And because this Renyi divergence between those matrices is exponentially large in their dimensions, this leads to a vacuous result. So given that at least some intuition here, we need a different approach for covering the decision variant of truncated LWE. And we give this by using hint LWE as an intermediate step. I haven't actually introduced hint LWE before, so I'll take the chance to do that now. In this variant, the adversary receives the matrix A as usual in LWE, but based on that now, the adversary is able to choose some hint matrix, capital H, which just has the restriction that the L infinity norm needs to be less than some bound, capital B, and then receives the regular LWE sample, as well as a hint, which is defined as the hint matrix times the secret plus some additional noise sampled from another distribution. Here, I'll focus on a setting where the secret and noise distributions are discrete Gaussians, and this is necessary because those reductions use decomposition theorems for discrete Gaussian distributions. So for this talk, I'll just ask you to believe me that there is a reduction from MLWE to hint MLWE when the error distributions are discrete Gaussians, and essentially all we need to do here is increase the noise. I won't go into why this is the case, but we're basically generalizing a known result to matrices, which is a direct adaptation of existing proofs, and you can take a look in the paper if you're interested. If we make use of that reduction, then we can give an additional reduction from hint LWE to truncated LWE to show hardness of truncated LWE based on standard LWE. And we can give this reduction as long as the distribution of the error from the truncated LWE problem is statistically close to the sum of the error and noise distributions from hint LWE. And we also set this L infinity, this bound on the L infinity norm in hint LWE to 2 to the C, where remember C is the number of bits that were truncated in the truncated LWE problem. Now I'll give some idea of this reduction. After receiving the matrix A, the hint LWE adversary B chooses the hint matrix to be set to the low order bits of the matrix it received. And then after receiving the sample and the hint, the adversary can compute and send the sum of the matrix and the hint matrix, as well as the sample and the hint, to the truncated LWE adversary, and then forward on the resulting guess. The first thing I'll point out here is that the L infinity norm of H is in fact 2 to the C, which is how we set this parameter B. And also the matrix A plus H is in fact the truncated version of the matrix A, so the sample sent to the truncated LWE adversary has the correct distribution. And now we can turn to the second part of the tuple, or the sample, where if the true underlying bit was 0, then the sum of B and H, the sample and the hint, will be the sum of the truncated matrix times the secret plus the error and noise samples. And as long as the distribution of the sum of the error and noise is statistically close to a sample from the truncated LWE error distribution, this can't be distinguished from a truncated LWE sample. And on the other hand, if the underlying bit was 0, then B is a random sample and H is independent, so B plus H is uniformly random. Next, I'll try to take some time and give a more detailed comparison between the two bounds that I just introduced, as well as some prior work. Like I mentioned, this is the same setting as the work of Jia and others, who provide a reduction from the slightly less standard module and-true problem and give a reduction for the search variant of the problem. Their reduction works for any secret distribution with enough min entropy, which is nice, but both the distribution of the starting module and-true problem and the final error distribution for truncated LWE need to be discrete Gaussians. So our work closes open problems left by them by providing a reduction from standard MLWE and also covering the decision variant. The advantage of the Renyi divergence-based approach that I introduced is its flexibility with respect to the secret and error distributions. It's a reduction from MLWE and works for bounded secret distributions and any error distribution as long as the corresponding Renyi divergences are defined and small. And examples that we give in our work of this are the uniform or the bounded uniform distribution, the rounded or discretized Gaussian, as well as the discrete Gaussian. On the other hand, though, I mentioned this reduction is limited to the search variance, so the public sampleability result is vacuous, and we rely on the hint LWE-based reduction for the decision variant. The biggest advantage here being that it could be applied in the context of NCPA public key encryption schemes for compressing public keys. Unfortunately, though, the reductions here make use of decomposition theorems of discrete Gaussians, so there's some restriction here. I didn't speak very much about the concrete parameters that are necessary for the distributions that we're talking about here for the reductions and the error distributions. But one thing I want to point out is that if we instantiate the Renyi divergence-based reduction with discrete Gaussian error, the loss in the ring degree for the error distribution is higher than for the hint LWE reduction. So that's one advantage of the hint reduction. Okay, so finally, to conclude, we give the first reduction from MLWE to the truncated MLWE problem and the first hardness reduction in general for the decision variant of truncated LWE. For the search variant, our approach using the Renyi divergence gives hardness results for many different error distributions. And for the decision variant, because the Renyi divergence approach doesn't work due to this public sampleability result being vacuous, we give a new reduction for discrete Gaussian error distributions using hint LWE as an intermediate step. One natural open question here would be to see if we can get hardness of truncated LWE for the decision variant of the problem without relying on Gaussian error distributions. It's not necessarily clear to us that there should be some fundamental challenge or gap here between finding reductions for non-Gaussian versus Gaussian error. And the reason that we do this for Gaussian error is just related to our proof techniques more than anything else, really. Thank you, and I'm happy to take some questions.
Thank you very much for the very nice talk. Are there questions for Hannah? If you have questions, well, obviously please raise your hand, but then also use the microphones in front of you, then I don't need to run around with the microphone. Let me maybe make a start. So, is it obvious that if you don't truncate, but if you round off, I mean, then you would basically introduce, for the same kind of space savings of the matrix, you would sort of lose a little less information. Is it obvious that the same arguments would go through for this, or is it obvious that they don't go through, and if so, for what reason?
That's a good question. I guess I would expect the same arguments to go through. I'm trying to think of any reason why they would not.
Okay,
Yeah.
I mean, that was also my
I'll
intuition. I was
double-check.
curious if it would actually go through. Yeah. Other questions for Hannah? Everybody's still waking up before the first coffee break. All right, well, if not, then please join me in thanking Hannah again.